Hello everyone, this is Xiaoyu Ji, an associate professor from USS Lab, Zhejiang University. Today I'm going to introduce our work, Poltergeist, Acoustic Adversarial Machine Learning Against Camera and Computer Vision. This is a joint work with the University of Michigan. In the very recent years, autonomous systems are booming, including self-driving cars, drones, unmanned ships, home and industrial robots. Autonomous unmanned systems are everywhere in our daily lives. For an autonomous system, computer vision has been the key to sensing the environment. In a computer vision system, cameras are first used to sense the objects around. Then the sensed results, such as person, stop sign, or traffic lights, are fed into object detection algorithms for detection. The detection results are then used to support driving decisions. Therefore, reliable computer vision is crucial to the safety of autonomous systems. However, if computer vision can be manipulated by an attacker, for example, failure to detect the front pedestrians correctly, an autonomous vehicle make a wrong decision like go ahead instead of take a turn or stop, then tragic consequences will happen. Adversarial examples that exploit the vulnerability of machine learning algorithms has been a threat against computer vision systems. Existing work in this area mainly focus on either altering the physical objects, such as attaching stickers on a stop sign, or just directly adds digital pixel perturbations on digital images. From the working flow of a CV system, we wonder whether we can achieve such an adversarial attacks by just utilizing the vulnerability of sensors. With this question, we take a close look at the autonomous vehicle's camera system. We find that a camera system nowadays utilizes image stabilizer to reduce image blur caused by motions. In the image stabilizer, the inertial sensor plays an important role by sensing the motions, and then the motions can be compensated on the blurry images according to the sensing results. However, the inertial sensors, such as accelerometers or gyroscopes, have already been reported to be vulnerable to resonant acoustic signals. This opens us the door and provides us the attack chance to generate adversarial example from sensors. So, following this philosophy, we propose Poltergeist. We manipulate the inertial sensor readings by acoustic signals, such that the images are blurred to be adversarial ones, which can be then misclassified by the detectors in a computer vision system. To investigate the feasibility of Poltergeist, we perform preliminary analysis by simulating different blur patterns and then feed the blurred images into detectors. We find that with different blur patterns, such as linear or rotational patterns we will introduce later, we can achieve hiding, creating, and altering attacks, which means we can hide something, or we can create new objects, or we can just change the label of an existing objects from A to B. So why will this happen? The behind reason is that a blurry image can change the outline, the size, and even the color of existing objects in the image, which contributes to the above three attacks. So although the results seem promising, we still face many challenges. The first one is how to quantify the impact of acoustic signals upon the blur pattern and blur levels. Another challenge is how to find effective and efficient blurry patterns to achieve targeted goals when we know nothing about the object detectors except for the detection results. That means we have to optimize blur patterns against black box object detectors. So for the first challenge, that is how acoustic signals affect sensors, existing work such as Walnut has shown the feasibility to manipulate inertial sensor readings by resonance of acoustic signals. Thus, we use the manipulated sensor readings to quantify the camera motions caused by acoustic signals. We especially pay attention to the motions along the X, Y, and Z axes of accelerometers and the rho axis of gyroscope to ease the burden of modeling the blur patterns. After that, the image stabilization module will compensate the non-existent camera motions caused by acoustic signals, resulting into pixel-level perturbation. We model three types of pixel motions, which are linear, radial, and rotational pixel motions. We also build a heterogeneous motion blur model to describe the blur patterns caused by motions from more than one axis. The visual appearances of the four blur patterns are shown in the four figures. Besides the first challenge, finding the most effective and efficient adversarial blurry image is neither trivial. First, the acoustic signals can be ejected from 4 degrees of freedom with different amplitudes, resulting in a large parameter space. Second, in the real-world attacks, we usually know nothing about the object detector except for their outputs, not to mention the gradient information for white box detectors. Third, as we inject acoustic signals into camera systems for adversarial examples, the examples are restricted by physical constraints like transmitting power. So to tackle this challenge, we first design objective functions for each of the attacks, taking attack effectiveness, cost, and physical constraints into consideration. Then, we use Bayesian optimizer to find feasible solutions. Bayesian optimization is a gradient-free method, especially working well for black box optimization problems. It takes the object detection results as input and can generate adversarial blurry images as we want. Combining all the above together, we design the Poltergeist system, and it includes 3 key building blocks, which are blur pattern modeling, attack parameter optimization, and sensor output injection. For a real-world attack, if the adversary has an image of the target in hand, the adversary first obtains the feasible attack parameter with the blur pattern modeling and the parameter optimization blocks. Then, the adversary manipulates the sensor outputs by injecting acoustic signals with the derived parameters to finally achieve the HA, CA, and AA attacks. To evaluate the performance of Poltergeist, we conducted both simulation and real-world evaluation. For the simulation evaluation, we use 2 popular self-driving datasets, that is BDD100K and Kitty, and generate adversarial blurry images with our models. Then we use the blurry images to attack 5 state-of-the-art object detectors, including 4 academic ones, which are faster RCNN, YOLO V3, V4, and V5, and also a commercial detector, that is Baidu Apollo. During the experiments, we take the following 5 objects that are person, car, truck, traffic light, and stop sign as our object of interest. First, in terms of attack effectiveness, the hiding attack, which is HA, can achieve 100% success rate against all of the tested object detectors, which means that HA can hide any object of interest, such as person, traffic lights, and 04, HA will be the most dangerous attack in real life. For creating attacks, targeted attacks are much harder than untargeted ones. Nevertheless, we can achieve more than 20% success rate for most of the detectors. Well, for altering attacks, just like creating attack, targeted attacks are also more challenging. Comparing altering attacks with creating attacks, the overall success rates are lower because creating from non-existing objects is more difficult than from an existing but different one. Besides the simulation evaluation, for the real-world evaluation, the attack devices include an ultrasonic speaker connected with a signal generator and an audio amplifier, and the victim device is a Samsung S20 smartphone running YOLO detectors. We also place a reference smartphone to provide ground truth without signal injection. The experiments are conducted on a moving vehicle in 4 scenes, including city lane, city crossroad, tunnel, and campus road. Here are the 3 real-world attack videos. The first one is hiding attack, in which a car is hidden during the attack process. In the second attack, we successfully created a non-existing trunk. And for the altering attack, a car is changed into a person. For more details, please refer to our website. We also compare the real-world images captured under attacks and the ones simulated by our blur models. Take a city crossroad picture as an example. The images during real-world attacks show similar blur patterns as the simulated ones for a same attack goal, that is, creating a bench from the zebra crossing. We also compare the success rates of 3 attacks in different scenes. We find that all 3 attacks are feasible. In particular, hiding attacks show the best performance in all 4 scenes, which coincides with the conclusion of simulation evaluation. In addition, we evaluate the attack distances. Attack power of 10 watts suffices to launch an attack from 1 meter away. To defend against the poltergeist, we can use safeguarding like shielding or add patch to the stabilization algorithms. In summary, we propose poltergeist, an acoustic adversarial machine learning against the camera and computer vision. More importantly, we summarize poltergeist as an instance of a new class of attack, that is, ample attacks. By combining the weakness in the physics of hardware and in adversarial machine learning to finally cause a system-level exploit. That is the so-called 4 ounces can move 1,000 pounds. That is all my presentation. Thanks for listening and welcome any questions.